Okay, well, we'll start the introductions as people continue to log in. Today we're having the AIPG Texas section monthly webinar. It is every third Tuesday of the month, so we hope you'll come back again next month. Today's webinar is History and Geology of an Increasingly Strategic Resource, and our presenter is John Berry. John has over 50 years of geological experience in metals and hydrocarbon exploration on 6 continents and in deep water basins offshore. During the latter part of his career, he specialized in the application of remote sensing techniques to on and offshore hydrocarbon exploration, as well as base and precious metals exploration. He holds an AB degree from the University of Pennsylvania and an MA in geology and geophysics from Columbia University, excuse me, where he worked in the Arctic section at Lamont Doherty Observatory. So we'll have our webinar today. At the end, after John finishes, in the chat will be a link to a quiz. If you want the AIPG New York State Education Department CEUs, you need to take the assessment quiz and pass with 70% or greater. You can take the quiz as many times as needed. To pass, you have 30 minutes. So half past the hour, when the webinar is over, the quiz will no longer be available. So take the quiz if you want the New York CEUs. Otherwise, as long as you are on the webinar for the full hour, you will receive AIPG CEUs if you do not take the quiz. So I also want to mention next Tuesday is the AIPG Lunch and Earn, and we hope to see you there. You're always welcome to check out the AIPG calendar on the website to see our upcoming events. And we encourage those that are not members to join. You save on all of the webinars and conferences that AIPG presents. So with that, John, thank you for providing a webinar today.
Thank you, Wendy. And thank you, everybody, for joining us, and welcome, everybody. Today, I'm going to be talking about the Central African Copper Belt, but my focus will mainly be on the Zambian Copper Belt. And the first outsider to reach Zambia from the developed world was Dr. David Livingstone in about 1871. And he came up from the south. So the first thing he saw was this, Victoria Falls, or in the Batonga language, Mosi Otunya. And it's about 400 feet high and well over half a mile wide on the Zambezi River. The Zambezi is flowing over a basalt plateau here and then plunges down into a canyon cut right through the basalts into the underlying schists. The 400 miles further north, Dr. Livingstone encountered the Arabs under a person whose name was Mushili or Munsiri, and he encountered them at this tree where they were conducting a slave market. So the tree was a great big beautiful tree then. It has since been attacked by a parasitic fig, and it looks like this now. So it's suffered somewhat the same fate as the treaty oak here in Austin. And the map shows where the falls are down there at the town of Livingstone, and Ndola is up here on the Copper Belt. So the next slide, the next person to come from the outside world into Zambia, or to affect Zambia from the outside world, was Cecil Rhodes. And he, of course, was trying to acquire his little private empire in Central Africa. And part of that was building a railway from the Cape of Good Hope up to Cairo. his railway got as far as, it got past the Victoria Falls. It got as far as a place known then as Broken Hill in Zambia, where there was a large zinc ore body, which was exploited early on. And so it diverted to Broken Hill and never made it much further. But it did connect with the railways in the Congo. So this is an aerial view of Victoria Falls and Rhodes's Bridge, and one of the huge locomotives that used to run on the railway. So this is a timeline, and I'm going to skim over it very quickly. You can download the slideshow if you're interested in more detail. But we have Livingstone in what is now Malawi over to the east here on the map below in 1860, and then by 1870 he was beginning to explore Zambia. After his exploration, the first other people to come in there was a mission established amongst the Lozi down here in the bottom left of the map, and amongst the Bemba up here top center. And then that was about 1885. About 1893, the British signed a treaty over the Congo, defining the border with them, because they couldn't have done that before then because they didn't know enough about the geography to define a border. In 1884, they had signed a treaty with the Portuguese, who claimed the whole area because they had long-standing colonies in Angola over here, Mozambique over here on the right side of the map, and on Angola at the left side of the map. The British said, no, we want the stuff in the middle. And then by 1898, the Burnham expedition, this was a geological exploration expedition led by an American, Dr. Burnham, explored the whole area, both the Katangan part and the Zambian part. And then a company called Tanganyika Concessions in London around 1900 got a mineral concession over the Katanga area here. In 1902, the British Crown claimed the whole area across the Zambezi, and in 1905, Union Minière de Haute-Katanga was incorporated to mine the copper in the Katangan area. What I didn't show on here is that, of course, the Katanga is part of what is now the République démocratique du Congo, and was ruled as a personal fief under the name the Congo Free State by King Baudouin of the Belgians. And this was a really very disastrous occupation. There was a lot of brutality against the Africans and whatnot. But that's who Tanganyika Concessions and Union Minière were dealing with, was the King Baudouin of the Belgians. So, and then to carry on the timeline further, just before 1900, a mine called Kansanshi was pegged in Zambia. That was the first pegging of a mine in Zambia. And then beginning then, 30 prospecting licenses were issued to small outfits. And I encountered some of these while I was there. Tanganyika Concessions was exploring the Congo pretty intensively. And by 1925, the British government decided, or the Northern Rhodesian government decided that they weren't getting anywhere with these small operators, so they negotiated with Anglo-American Corporation, that's the Oppenheimer interests, and RST, which was Chester Roan Selection Trust, Chester Beatty, to start big systematic prospecting campaigns on the Zambian side. And that's what they did. So this ended up with the Bwanamakubo mine first opening in 1920, not lasting very long, and then the Roan Antelope, the Nkana, the Nchanga, Mufulira. These were huge mines with, producing, in my day, producing 100,000 to 300,000 tons of copper a year. And later on, there was Chibaluma and Bancroft. So one might ask, why did it take from 1873 until the 1930s to get anything going in Zambia? And there were several reasons. One is there was no infrastructure. The railway got as far as Broken Hill, which is about here, right under the B of Zambia, and that was it. There was nothing else. The other thing was that until 1900, the political situation was not stabilized. The European powers were all competing for bits of Africa. So that sort of deterred people. And then there were the limitations of the place itself. The shaded areas on this map are areas where tsetse fly is endemic. And tsetse flies transmit sleeping sickness, for which there was no cure. And in those days. And then the entire area, everything on this map, was endemic malaria, very bad kinds of malaria. Livingstone himself died at this lake in Zambia, Lake Bangweulu, just where the X is, of blackwater fever, which is what you get when your internal organs pack it in from malaria. There was also schistosomiasis was everywhere. That's flukes that spend part of their life in snails, in water, transmit that to humans, and it's very, very long, drawn out, painful, and fatal. Bilharzia, we called it in those days. Then there was elephantiasis, and leprosy were quite common. I had workmen die of these diseases. Then there were parasites. Everybody was loaded with parasites, and then annoying things like botflies. Plus, all of the crocodiles, hippos, lions, tigers, and all of these wonderful snakes. People were not too eager to go to this part of Africa. And this is a map of Western Zambia put out in 1919. By that time, the British had been well established there for about 20 years at this point. There were only 3 missions, 3 government posts, and 3 farms, a Welsh farm up here, Taff Vale Farm, a Scandinavian-owned farm here at Winilunga, Rickberg's farm, and Austin's farm near what is now Ndola. So, and that was it. And 1 closed mine. Kansanshi had opened, and it had closed. So about 1929, 10 years after this, out came Julian Feiss from the United States with his master's degree in mining from the University of Arizona, joined Anglo American, and had to walk basically from Kabwe, which is off the map, down at the bottom of this red area, up to Austin's farm, and then from there to Kansanshi, which is about 105 miles, and then down to Kasimpa, back and find a way of getting across the Lunga River to the area he was assigned to explore, which was the Chifumpa area here. And the reason he had to walk that long way is because that's the divide between the major rivers, the Kafue, the Lunga, and the tributaries of the Zambezi. So he followed the divide until there was a ford on the Lunga, and then carried on. The red outline is the outline of the modern Copper Belt. So this is Julian Feiss near Chifumpa in 1929. And the reason I have these, I'm talking about him, is I knew his father. His father was Jeffrey Feiss, and sent me Julian's autobiography of his time in then northern Rhodesia. So this is I took this photograph, but this is my friend Stan Krowski and a guy called Sherman Drake. Sherman had been bringing, Stan was the mineralogist on the mine. Sherman had been bringing in samples of rich ore from some unknown location 90 miles from the nearest road. So Sherman decided, Stan said, well, I want to see this, where these are coming from. So Sherman had this road built out by a gang of people so that we could drive the 90 miles from the real road down into the Luangwa Valley, which is this Karoo Rift. When when we got to the end of the road, this is what we found. There was the men prospecting. They were actually on, it was a Sunday, so they were making guns, copying this. This is a gun with a gun stock here, and he's copied that gun stock into wood and it's making a new gun. The barrels came from car steering columns. The flint locks that came from the metal in the flint lock came from car automobile springs, and the actual flint was traded down in Arab dhows down the East African coast from very close to my home in England. This is what his camp, this is Feiss's camp at Chifumpa looked like, and this is what a similar camp looked like 20 years, 25 years later in my prospecting area. And these are the foundations of those round huts, which we call rondavels, all gone back to nature. There was an oven at this old campsite that was carved into an anthill. So you put your bread and stuff to be baked in this tunnel, and then you lit a fire under it and blocked up the ends. And there was a chimney for the smoke to come out. So there was still some illegal, illicit, and minor mining going on in the Chifumpa area when I was there. And one weekend, my late wife, my colleague, Case Borghouse, and his wife, and the mineralogist, Stan Karowski, we went out to look at these emerald mines. Everybody knew about this emerald mining, but nobody had been there because it was run by an Afrikaner, a South African, and his nephew, and they did not welcome visitors because they were smuggling the emeralds out of the country to get them. They just loaded up a Land Rover with rock and took that down to the border, and then got the emeralds out over in Rhodesia, where nobody was interested in stopping them. So that was the Miku area emeralds, and here are the other emeralds, and the Chifumpi Copy or hill, which was the center of Feiss's exploration area, is right there. I just put in here this lime quarry, which is in Precambrian limestones, just predating an ice age. And here we're drilling for water. I had to bail one of the crew members of one of these people out of jail because they were accused of killing somebody over a chicken. This is Feiss back in the 30s, and he's down in exploration. Somebody's down in exploration pit here, and they've got this headgear to lower him on. This is what the pits look like in the bush. This was out at Kansanshi, which is that mine I spoke about. And when they dig these pits, they separate what comes out according to the rock type. The Africans are good geologists. So that's the ore shale. This is the dolomites, and this is samples of malachite that they dug out. And then here's me getting, the pits in the old days were rather large and they were square. We'd found out that wasn't safe. So ours were much smaller, only about 2 foot 3 inches in diameter, and they were round. And here's me getting ready to go down one with my shift boss and my sampler looking on. And if we found good values of copper down in the pit with them, we sampled the pits using these tapes to mark off sample intervals. This is looking directly down a water-filled pit about 35 feet deep. So if we found values, then we cross-cut between adjacent pits. So we dug a tunnel through, and these tunnels are about 2 feet wide and 3 feet high. And there's my sample at Chishimba inside one of the tunnels. Why did we have to do this? Well, because this is what the rocks look like. Central Africa has been an uplifted plateau since the Jurassic. The weathering is very, very deep. There are really no hard rocks down to a depth of about 450 feet. And we're looking here, the top of this face is at 40 feet depth. It's in Bonamakubwa mine. And the base here where somebody's standing is 80 feet deep. This here, the top, you can just see the bottom of the B soil horizon. Then this is all C soil horizon. Weathered bedrock just turned to clay. This was a dolomite. very contorted dolomite. This hanging wall stuff here was a gabbro, and it's weathered even more deeply than the dolomite. This on the top right here is Feiss's picture of the office at Nchanga mine, which was already beginning to be developed. But that was the office and settlement, basically. In 1966, Nchanga mine, when there was an underground mine, but the surface mine looked like this. And by 1973, it looked like this. In 1973, it was one of the largest open cuts in the world. It was about 1.5 miles long and 700 feet deep. So, and then just this is Feiss's exploration camp in Chifumpa. This is mine at Makuba 30 or 40 years later. This is the mine office, which was built 6 years after Feiss's experiences when they opened up Nkana mine, which I worked on. And the architectural style is called Cape Dutch. This picture was taken in 2012, and I got it from the web. So this is what I was living in that camp for 6 months through a whole rainy season. And one morning I got up thinking there was a snake inside, and I leapt up vertically and got out. And what I found was my tent was being eaten by ants. And so these are army ants. And we had to dig a big ditch around the whole camp, essentially, and fill it with ashes to keep the ants away. This is my kitchen. This is one of my dinners. I ate that mushroom. This is typical transport in the marshy areas, dugout canoe. And this is the famous copper flower, which was a major exploration guide in the very early days, because this only grows where there's more than 500 ppm copper in the soil. So Kansanshi mine, to open it up in 1908, they had to build a cordwood road from Cowboy, which is off the map, and then follow the same route as Feiss did in 1929 along the watersheds to the mine. But this is a 400-kilometer long road made of logs lied adjacent to each other so that a large steam road vehicle could travel over it. Now, the copper discoveries were not discoveries as such. Kansanshi mine had been mined extensively by the Africans, as had Bwanamakuba, where I worked. And the Africans were very good miners. They took out the copper-bearing veins, 25% copper in these veins, and left the wall rock completely undisturbed, clean as a whistle. And they went down all the way to water. The one thing they could not do was they didn't have pumps. They couldn't pump water out of a mine. So at Bwanamakuba, the water table was at 176 feet, and they went all the way down to it. So the Kansanshi was opened in 1908. They even hauled a small smelter out to save having to truck ore to civilization. And it went bankrupt very quickly. It was only open a few years. It was reopened in 1955 using for a power source the engine from a scuttled U-boat that was in Cape Town Harbor. And it was flooded out again within 2 years. So it had a very checkered history. It is now the largest copper mine in Africa. The Africans, when they mined it, cast the copper, which was malachite, was actually what they were mining. They roasted that and they got the copper out and they cast it into these crosses, which were traded by the Arabs down to the East African coast of Zanzibar. This is what the mining looked like underground at Nkana mine. At one point, they came to me and they said, John, we think we may have left some ore behind in a syncline that we didn't know was there. Can you get out there and work 7 days a week and explore it by pitting? So I did. And the mine shaft over here, south ore body shaft at Nkana, was 1 mile deep. So I'm pitting along the top and I'm actually making crosscuts underneath the railroad and all sorts of stuff and working. One day I got caught down one of these pits in a crosscut, actually, when they blasted 400 feet directly below me. That was not pleasant. This is the smelter in those days was treating 300, was producing 330,000 tons a year of copper. And this was what it looked like inside. This last picture here is collapse over a stope. They used sublevel caving as a mining method. They left nothing behind, so there were no pillars holding up the roof or anything. It just caved in after they passed by. So what they did to prevent the water flowing into the mine through these caving holes is every one of the mines built up these huge tailings piles from their smelters, from their concentrators, and piled up tailings on top of the caving areas to make them into hills so that the water would run off, and the tailings being very relatively impermeable, the water would run off away from the caving areas. The only trouble is that sometimes the caves were very sudden and big. And in this case, one happened at Mufalira in the middle of the rainy season. This big hole formed. The whole tailings pile went down it. The tailings liquefied into a slurry, and they went down through the caving cave stopes into the mine at the 1,500-foot level, and 89 men were encased in mud down underground. Another disaster, and the mining was relatively safe. I mean, compared with British coal mines, the mines in Zambia were safe, but when there was a disaster, it was big. This one is a train driver got drunk with a train hauling 6,400 tons of gelignite, and they brought explosive experts up from all over Southern Africa and removed 78 of the 80 cars, but the last two were too smashed up, and the rain had gotten to the gelignite, and so the only thing they could do was blow it up. So this is 160 tons of gelignite as seen from my house 12 miles away. A little mushroom cloud. Other disasters, the Kavironda Amfex plant, somebody was smoking probably while unloading a train. 30,000 tons of Amfex went up, and there was nothing left of the factory or a huge village. Nobody knows the death toll. Wanky Colliery, the whole management team went down to the horse races in Johannesburg one weekend. The people that were left behind failed to keep the dust level in this the colliery coal mine down, and when the mine management came down and made a tour of inspection on the Monday morning, the whole mine blew up, and there were 426 dead, including the entire management team. This was the mine that supplied all the fuel for the smelters in Zambia and in a large part of the Congo too. The last thing, this made international headlines, that Dag Hammarskjöld, United Nations General Secretary, was landing at Ndola Airport in the course of a peace mission to the Congo, where the copper-rich province had seceded and there was vicious fighting going on. His plane crashed, he was killed, and this is the memorial park at the site. And there's still all kinds of conspiracy theories and investigations going on about what happened. That was in 1961. So as oil is for many, many countries, copper was Zambia's curse and Zambia's blessing. We're looking about 1934 was when the first copper was produced. Production rose steeply through the end of the war. After the end of the war, there was a decrease. Then there was another huge production increase with very high prices at the peak of this production increase. Then prices went down drastically and until 2000 and something, and then they started coming up again. The Zambian government, because of political reasons, nationalized the copper minings at the peak of the price here. So they bought high, they paid full price for them, they bought high, and when they gave up and sold them off again just before 2000, they sold low. So this was a real curse to the Zambian government. The falling copper price was caused by the discovery of many porphyry coppers in Latin America. We had gotten to understand in this time period, 1970 on, to understand the geology and the occurrence of porphyry coppers really well. And they were easy, they were near the surface, they were huge things, very low grade, but amenable to low cost surface mining. Zambia's mines were largely underground, high fixed costs, couldn't compete with that. But also, after they had nationalized the mines, a lot of the skilled workers, skilled expatriate workers that they depended on, left in a hurry, and because they could see that they were not going to be working under the same favorable terms, and and there had not been enough Zambians at that point trained, so they had a severe skill shortage. Plus, at independence, 6 years before nationalization, the Zambian, when Rhodesia declared independence unilaterally, Zambia closed the border with Rhodesia, and the only railway, the main railway went out through Rhodesia, and the main roads went out through Rhodesia. Other routes were through the Congo, and by 1970, the Benguela Railway through the Congo had been destroyed so many times by Angolan terrorists, because it also went through Angola, that Zambia was really stuck in terms of getting its exports out of the country. I'm going to save time by not going into this, but the important thing is that when we have a certain type of ore deposit, grades tend to decrease with time, and then you discover something else with higher grades, and you mine it, but grades decrease with time again, because you always mine the best deposits first. And this is going to be important in terms of what's going on in Zambia now. In the plate tectonics, I'm not going to go into a lot of detail here, but these three up here are Crisco-Tizzi reconstructions. So what he's showing is the craton consisting of the Congo and Brazil, already merged at 1 billion years ago, which is fine, but colliding with it's West Africa. I'm sorry, I'm not looking at the thing I thought I was looking at here. It collides with West Africa at about 1 billion years ago, and that to me is really wrong, because the evidence of this orogenic belt, which is showing the collision between the Congo craton, the Kalahari craton, the Antarctic craton, and the Australian craton, this is all going on at about 580 million years. So this is way too early. We got the Kalahari craton here in West Africa colliding, and that's wrong. Then again, he shows the final closing up of Eastern Gondwana at 800 million years. And that's this origin, and this origin is a little bit later than that, but it's still just around 500 million years ago. So I'm a little leery of Chris's movies of plate tectonics here. But essentially, what we're looking at in Zambia is that the closing between Kalahari craton and maybe Antarctica as well, and the Congo craton was just before the beginning of the Cambrian, and resulted in this Lufillian arc here. And that's what the copper belt is in, this Lufillian arc. So this is the regional geology. I'll go back to here a minute. This area here is called the Eremite belt, and this area here is this isn't the Eremite. This is the Eremite here. And the regional geology is this. Here's was the Kibaran belt, and I lost the word for a minute. These are 1.1 billion year old mountains, and these are 1.3 billion year old mountains. And the primary rock type that we see in outcrop is a very, very clean multi-generational quartzite here. Then at some time around 800 million years old, an alacogen, a failed arm, opened up here between the Benguelu block, whose basement is about 2.2 billion, and the Kibaran belt at 1.1 billion. And so it opened up, and so an incipient ocean formed down here where the Kasempa block is now. And then around 600 million, things began to close up again. And we begin to get this happening. So we have the Katanga High here, which is largely intrusive, coming in and overriding these sediments, which go from very continental sediments here out to shallow water sediments with lots of evaporites here into a deeper water environment here, and then you start getting a lot of intrusives here too. And so you have this low angle thrust belt developed with the Katangan, the lower part of the Katangan series here, riding out into very, very extensive nap sheets, because this is a couple of 100 miles that are where the columnar horizons are salt from that was deposited early in the history of the Katanga deposition. And then in this belt, the dark blue belt, so that's the thrust belt is this pale gray belt here. And then the dark blue belt is the domes belt, which has apparently been dragged down into a subduction zone at some point, and the depths recorded are up to about 85 kilometers. The metamorphic grade mineral assemblages suggest depths of about 85 kilometers have been reached here. And then overlying that is a slightly younger series of rocks. These do not correlate with the rest of the Katangan, and that's in what they call the synclinal belt. So we had a subduction zone over here that was pushing in. There must have been another one here for a while that this partially got subducted into, and then this huge thrust belt. And this blue line that I put in here is going from, because we go from very incipient metamorphism here at the eastern edge of the Copper Belt, about 10 kilometers depth of burial or less, to 85 kilometers depth of burial over here. So think of the thing at the end of mountain building, you have to tilt it down 30 degrees on the right-hand side. The more modern developments, we had the Karoo rifting, that's Carboniferous Permian age rifting, that occurred here in the Luangwa Rift and up here in the rift up in Tanzania. And the Zambezi Depression is of Karoo age origin, and the Limpopo Depression too. Then the continent in the Jurassic was uplifted and all this incredible weathering began. And then in the Miocene, we started to get the modern East African rift with the Tanganyika rift, the Nyassa rift, the Rukwa rift, the Luapula rift, the Luangwa rift was rejuvenated. The Zambezi Depression was rejuvenated, and so was the Limpopo. So between these rifts, what the blocks, the Kasempa block and the Benguelu block up here, and the Rhodesian block, they all became saucer-shaped with raised edges that are filled with swamps. So here in the Benguelu block, we have Lake Mweru, where Livingstone died, and in the Kasempa block we have the huge swamps along the Kafue River, the Kafue Flats. The Zambezi River worked its way up the Zambezi Depression, cut a canyon through here, and then around the edge of the Kasempa block and up into the Upemba Rift. But its tributaries have carved into the center of the Kasempa block and drained some of the marshes. And the Kafue River, which drains the Copper Belt, has done the same thing. So this is the more detailed geology of the of the Copper Belt, the whole Copper Belt, including the Katangan part of it, Congo part, and the Zambian part. And I'm calling this the old Copper Belt down here on the bottom left, right. And the new Copper Belt is the Copper Belt in this domes province. These are basement domes, Luswishi Dome, Solwezi, Mombeshi, Kabompo Dome. This is called the Kafue anticline, and it plunges down to the northwest here. And here are these contours of depth during metamorphism. And so we have chlorite grade here, and we have metamorphism, and we have white schists here, which are the equivalent of blue schists in very argillaceous rocks. And that's what these deposits are these white schists. And you can see in the Kafue anticline, we have these basins of Katangan rocks. This is the Chambishi Nkana Basin, this is the Rhone Basin, and this is where Nchanga is in this little basin, which doesn't have a name. And you can also see that these basins have got tight folds at one end of them. And as you go away from the Kafue anticline, you get these narrow, long, elongated faults that probably originally were salt cored up into the Congo, and where in the outer parts of the Lufilian arc, these things are now left as just the rocks in the cores of these faults are now left as isolated klippen. This is Nkana South open pit, which is here near Kitwe. And in 1971, this was the rush job I had to do, was to delineate this ore so that they could come in and mine it before they undermined it. And this is the kind of structure you see there. This is not my drawing. This was drawn after the pit was made. But we see tight anticlines in the dolomitic hanging wall here. This is the ore shale, carbonaceous shale with copper pyrite in it, mostly chalcopyrite. Another parasitic fold there with a black core to it. And then here a core in the footwall sandstone, a tight fold in the footwall sandstones. So very, very tight folding. Some people say that part of the reason for this tight folding is that these original depressions these rocks were laid down with have been inverted. This is this section in Nkana further south where the folding is even more spectacular. The black is the ore shale. Here's the scale. The ore shale is generally about 40 feet thick, where it's undeformed. And here you can see it's all kinds of thicknesses. This is the footwall quartzite, which goes from nothing here because there's basement in contact with the Katangan here, and it's several hundred feet thick here in the syncline. So this is the flanks of a hill. There was a uranium deposit in this area that some of the uranium went into the bombs during World War II. This is the Rhone Basin, and this is the sort of less folded part of it to the north, and this is the southern part where it looks very similar to what I've just been showing you. So you can imagine that we try to pitting and cross-cutting is a very slow method of exploration. We tried a lot of things other than that. We had to do it. We had to do something because there's no outcrop in my whole 16 square mile concession area in the Chambishi Basin. There was about 8 square feet of outcrop, and it probably wasn't in place. And so during the 50s, they looked very hard at geophysics. And the problem is nothing worked because gravity doesn't work, because these are all, you're looking for copper in sediments, and gravity isn't very susceptible to, there aren't great density differences in these sediments. They try to use induced potential, but we don't have igneous rocks. Same with magnetics. There's no igneous rocks, so there's no magnetic signature. signature. Seismic in those days just absolutely could not address dips as steep as that. So the only thing that really worked well was geochemistry. And there were mining companies worked with a team at Imperial College in London to devise very efficient ways of doing regional soil surveys, doing stream sediment surveys, and we also sampled all pits and crosscuts from the surface to the total depth. Everything was run for copper and cobalt using atomic absorption. And now this is a more detailed, it's the same map essentially, but it's a more detailed look at the Copper Belt. Here's the Chambishi Basin with the Ancana syncline at one end. There's the Rhone Muliashi Basin with the Rhone syncline at the south end. These mines are the big mines in my day were the Rhone, number 3, the Ancana mine, number 4, Chambishi mine, number 7, Nchanga mine, number 11, Bancroft mine, the wettest mine in the world, pumping 90 million gallons a day, number 12. 13 hadn't been opened, and some of the others were small. Oh, Mufalira was huge on the other arm of the syncline. Kansanshi was being explored again. And the problem with Kansanshi and the mines out further to the west was, and also with some of these surface shallow mines here, was that the copper was not in the form of an oxide or a sulfide. There were methods for treating those things. It was in the form of silicates and mixed in the matrix of manganese wad. Manganese wad composed 15% copper. It was in micas, it was in vermiculites, and mining companies were trying desperately to find a way to treat these ores. So now I'm switching out to the new copper belt, Kansanshi mine out here. That's Holwezi. I was responsible for overseeing the exploration of this mine for a year or two. The reserves are nearly 1 billion tons. The grade is 0.66 Cu. So back in the old copper belt, our grades were 3% on average. Our cutoff was 1%, but the boundaries of the ore bodies were kind of sharp. And once you got, 50 feet into the ore body, it was uniformly 3%. Very, very regular. But they're down now half an order of magnitude from where we were. They're also way out beyond the infrastructure. There's no railroad out there. There's a road of sorts, 100 miles. It was a terrible 100-mile long dirt road when I was there. I think they have a real road now. They also have some uranium in the ore body. It's still mainly a vein deposit. There is disseminated rock, the copper in the wall rock, a considerable amount of it. There's also secondary supergene copper, malachite draping the sides of karstic depressions. So that's the oxide ores. And then there's the mixed stuff, all these wads and vermiculites and things. So what they use is sulfide flotation for the sulfides, and then a leach processed for the mixed ores and the oxides. They have a smelter that can treat 1.2 million tons of ore a year, and its output is 300,000 tons of copper a year, which is about equal to the Ancana smelter when I was working there. And then they put out 120,000 ounces of gold every year. Every bit of SO2 from the smelter is captured. As we talk about CO2 capture and storage. Well, they've been doing it for SO2 for 50 years. And then that yields 1 million tons a year. 1 million tons a year of sulfuric acid, which is used in the leach process. They use these Hitachi trucks, but they've got a new wrinkle on them. They have trolley wires leading out of the mine. So the trucks, they're diesel electric trucks, they run on their diesel engines down in the mine where they need a lot of maneuverability. But when they start coming out, they hook up to these wires, they go to completely direct electric drive, which decreases their fuel consumption by 90% and increases their speed by 100%. Very efficient way of doing things. Lumwana is a mine. It's had a rather checkered history. On the next dome out, that's the Mwambeshi Dome, even less infrastructure, owned by Barrick Gold, 500 million tons, but with a grade of 0.55% Cu, so even lower than Kansanshi. But it also has uranium, gold, and cobalt. It consists of 5% of disseminated sulfides. That's 5% of the sulfide mineral, not copper, in these white schist metasediments consisting of muscovite, phlogopite, quartz, and kyanite. They do sulfide flotation out at Lumwana, but they smelt at Nchanga. They truck the ore into the old copper belt for smelting. And as I say, it's been closed down a couple of times and it's had a checkered history. The Sentinel or Kalumbila project has 1 billion tons of reserves at 0.51% copper, lower again, and even another further 100 miles out into trackless bush. Well, there's a road, there's a dirt road, but it's no electricity, no nothing. And it has a good stripping ratio, though, to 2.23 to 1. And the ore is in Rhone metasediments now. And it also contains copper, cobalt, and gold again. Nickel, cobalt, and gold, I mean. So this is the stratigraphy, and I've been beating around the bush about stratigraphy. But here we have, this is sort of a composite of Zambia and the Congo. We have the Kibaran basement, 1.1 billion years old here, and represents the results of an orogenic event. So there's a lot of granites and things in it. But then at 800 million years, it started rifting. So we have a continental rifting event starting starting around, they say 900 here, but I think most people accept 800. And then the rift, you get these ore-bearing sediments in the lower Rhone, which record a desert climate, and the gaps between them are where they infer there were large salt horizons. So you have silicious, silty dolomites with salt beneath it, and then you have more salt, and then you have dolomite with a siltstone, a chloritic siltstone, and then more salt, and then more dolomite and siltstone, and then a lot of salt and dolomite and black shale, which is actually the old copper belt ore formation. And then you go up into the Nguba group, which we used to call the Marsha group. And at the top of that, sorry, not at the top of that, at the bottom of that, you have the Grand Conglomerat, which is a dropstone conglomerate, very thick, and that represents the Stuartian glacial epoch. And then at the top of the Marsha group, you have the small Petit Conglomerat, which is another conglomerate, a glacial conglomerate, and represents the Marinoan glacial epoch. So the cryogenic period, snowball Earth period, is embraced or represented by the Marsha group, with a big conglomerate at the bottom and a smaller one at the top. And so what has happened during this Rhone sedimentation is you've gone from a hot, dry desert with evaporites down to glacial, so periglacial conditions. And this little ocean that had developed was full of icebergs dropping things to the bottom. And then the Kundalungu is mostly dolomite, shales, and siltstones, very thick sequence, and that caps everything else. Some people think of the lower part of the Kundalungu as what they call a cap limestone now. So, and then what you have in northwest Zambia again around 600 million, you're getting now deep burial and metamorphism. So you're getting eclogites out in the Domes province occasionally. And then we end up at 530 million with the Hook granite, the Katangan High Hook granite massif, very huge, and also peak metamorphism. And then from 500 on, we're into a period of post-orogenic cooling. We used to make big efforts to find fossils in the Kundalungu, and I believe they have found those late Precambrian soft-bodied fossils there now. So looking at the structure of the old copper belt in more detail, these are the structural directions in the Iramide belt. It runs sort of west-southwest to east-northeast, and tight folds, very tight folds. And then they sort of die out northwards, and they only extend to about here. They don't even show up well on this map. And then you have the Kafue anticline, and you're getting these northwestern folds in the Katangan series that belong to the Lufilian arc. And so, and there's been a lot of talk about how the rift faults that we know were associated with this 800 million alakagen up in this area actually control the structure. So I tried to restore the structure for the central part of this anticline using a series of 6 cross sections.
John, I'm sorry, John, I just want to give you a heads up. We're about 3 minutes before the top of the hour.
Oh, right. So and I came up with this, where you see that the faults are in the Katangan direction, and you still have folding up here in the Iramide direction. So here's the model, and this is about the end of it. You have a Great Basin type fault. In these faults, we have found a few mafic intrusions with copper, cobalt, nickel in mineralization. You have brines being generated in these playa lakes and salt lakes, and they sink through the porous arenaceous substrate here, filling the valleys. Then they rise up underneath the freshwater wedge and are forced through the reducing sediments of the black shale and the Sabka things. And then in more detail, you have this picture where you have barren gaps over the basement highs, and then you go out through a zoning of chalcocite to bornite to chalcopyrite, and then into the peritic carbonaceous shale. And on the next block over, in this case, you have some ore bodies in fluvial sediments below the base of the oil shale. That's the Chibaluma ore body. This is more detail of the same thing for anybody who's really interested. We have one deposit in the United States, the White Pine deposit in the Upper Michigan Peninsula, which was very similar, with the ore in a reducing shale, a porous Copper Harbor conglomerate below it, which was pinched out over a basement high and forced the ore-bearing waters, presumably coming from the same sources as those lavas with native copper in them, pushed it up through the ore shale, so the ore shale got a high copper content there. And that mine, I was just reading recently, there's a new mine being opened next to White Pine very shortly. And here's my epilogue. I'll read it very quickly, hoping that it won't go too long. This is by Julian Feiss when he got home to America in Changa, where PhD rubs shoulders with the illiterate driller, where a scion of aristocratic British nobility raises his glass beside that of an Irish lorry driver, where a drunken, bleary-eyed silent man plays Beethoven's Moonlight Sonata or Grieg on a wheezy piano, and later goes back to his job of engine driver, a story in itself. There are young and old, clean-looking English boys, bronze Australians, hard-bitten Americans from the mines of the Seven Seas, quiet South Africans, amusing Scots, noisy Irishmen, perpetually drinking. It's full of stereotypes. Active, keen Canadians, Belgians, Germans, Frenchmen, and finally the inevitable black person. There are gentlemen, scholars, muckers, carpenters, mine bosses, drillers, lorry drivers, storekeepers, a few of the explorers, a queer, quiet lot we are thought to be, office force, draftmen, native police officers, surveyors, construction engineers, pump drivers, assayers, maintenance, fitters, and the inevitable traveling salesmen, contractors, and finally, a lot of just plain bums. Thank you.
Thank you, John. That was a quick overview of that, or going through that. That was very good. We had a few comments. I did put the quiz in if anybody's wanting to do that. It'll be available for
Yep.
30 minutes, and you must get 70 or greater. And you can take it as many times as needed to pass that. So we had a couple of questions real quick here. Let me
Yeah,
go
let's
back
do
to that.
Yep.
Could you tell us more about the conspiracy theories regarding the explosions?
There's some people think the CIA, a lot of people think the CIA had something to do with getting that aircraft shot down. There are other people that think that the pilots had been drinking and there's a town in the Congo called Ndolo, and they think that they pulled out the wrong maps and tried to fly into Ndolo. And actually, I plotted their flight path, and it makes sense in those terms. So, but the trouble is, at Ndola, there's a hill where there should be a clear flight path for Ndolo. So the Swedish government is reinvestigating this CIA theory. I don't believe it, and nor did my forester friend who was responsible for the crash site. I mean, he was managing the forest where it happened, and he was there not at the time of the crash, but within a few days. And he didn't think it had anything to do with. There were stories about, the plane was full of bullet holes that came from the outside, whereas it actually was full of ammunition, and the ammunition exploded during the plane fire, and the bullet holes were all pointing outwards, according to my friend.
Mm-hmm.
So anyway.
Interesting. Let's see. Russ says, I now see the demise of this Southern Rhodesia copper industry.
Oh.
Very interesting. Oh, somebody said, what does mined and then undermined mean?
Oh, mined and then undermined. Well, if you're mining underground and you mine underneath ore that is above you, and then your stopes that you've mined underground collapse, then you can no longer mine that ore above you. And that's what they were afraid of. They were afraid that there was this shallow surface ore that they would want to mine by open pit methods, but they were undercutting it so that it would end up in subsidence cavities.
Mm-hmm. All right. I don't see any other questions or comments. So that's all right. They say very interesting, amazing. Loved learning more about mining in Africa. What a wealth of information, John. I agree. Amazing.
Yeah.
Well, thank you very much. We appreciate everybody attending. We've hit past the hour, so we will put it into the webinar. And thank you very much. Remember, Texas webinars are every third Tuesday of the month. So come back and see us again. Thanks, John.
Right. Thank you, Wendy. Thanks, Kathy. Thanks for staying.